Hi everyone, in this video we're going to be looking at the derivative of the tan function. So we'll start off with a little recap on what tan of x actually is. We'll move on to graphing the function of the derivative by the original graph of tan of x, and then we'll look at the formal rules of derivation for y equals tan of x and more complicated versions like y equals a times tan bx plus c. So starting off, what exactly is tan of x? Well, tan of x I think is easier to understand than sine of x or cos of x, because all it is the gradient of a right angled triangle where x is that angle there. So it's the gradient of that line in particular. So a lot of people intuitively will say, okay, if x equals 0 radians, the gradient tan of x is going to equal 0 because that triangle looks something like that. If x is equal to pi on 4 radians, which is, I'll put it down for ease, 45 degrees, because radians times pi on, radians times 180 on pi equals degrees, and degrees times pi on 180 equals radians. Well, the tan of 45 degrees is saying, well, the tan of pi on 4 radian is saying what's the gradient of a triangle with 45 degrees, and that is going to equal 1. So think of tan in those terms. Let's have a look at the graph to the top middle of the screen there. That is the tan function all graphed out, and that's saying, well, at 0 radians, the gradient 0, and at pi on 2 radians, a lot of people say this is incorrect, but they say, well, it has an infinite gradient. Think of it instead as an undefined gradient. As x approaches pi on 2, from numbers less than pi on 2, yes, it tends towards an infinite gradient, but it's actually undefined there. So let's have a go at graphing what we think the derivative function is by looking at the original function tan of x. I'll do it in red, so dy dx will be in red. Well, first of all, something we've got to realize is that there are no stationary points in this graph. The tangents along any point of this graph are not horizontal, and even more than that, they are not negative. There's no tangents that look like that. So we can say, okay, the derivative function is going to exist above the x-axis in the positive dy dx values. Another thing we have to recognize is that the minimum gradient, so the least steep part of the graph, occurs here, but it's not 0. So that should be the lowest point of the derivative function. And we can mark that in, say, here. So we'll put a few points in. That's the minimum gradient, and it only gets bigger from there. So going by this graph here, there's the tangent at x equals 0, and here's the tangent at x equals, say, pi on 4. It's actually getting bigger. So this derivative function is going to increase like that. And it'll do the same thing on the negative side because these tangents down below are also getting steeper, more positive. Here, I guess, since this part of the graph is identical to this part, it behaves the same way. And since this part of the graph is identical to this part, we can just mirror that. So as you can see, the derivative function repeats itself every pi intervals. Now the mystery is, what exactly is this function that we're seeing in red there? And I'll jot it down on the left. Y equals tan of x, then dy dx is equal to 1 over cos of x squared, and this is shorthand written as 1 over cos squared x. So don't be intimidated by that cos squared x. That's simply cos of x squared. Okay, so let's see how we can graph that function if we know what the cos of x function is. So I'll have 3 colors going on these axes down below, y there, x there, pi 2 pi. And the first one I'm going to do in green is y is equal to cos x. I'll mark in the points 1, -1, pi on 2, 3 pi on 2. Here's cos of x. Let's get that fairly accurate. There we go. Notice I'm not drawing it as if they're half circles, which is how some people draw it, because the gradient is not infinite there, so never draw it as half circles. It's always got a nice curve to it. Now we want to draw the next function, y equals cos squared x. Well, if you square a negative number, it becomes positive, so we expect these points down here to jump above the x-axis. And if you square a number that is 1, you just get 1. So these points will not move. If you square -1, you get positive ones. This point will move to here. And here's the important thing. If you square a fraction like this, 1/2 squared, you get a number that's smaller. So for all these points on the graph that are less than 1, here, here, they are all going to move down a little for this yellow graph. So let's try and graph that. 1 stays the same, 0 stays the same. This point will jump to +1, -1 squared is +1, 0 remains the same, 1 remains the same, and everything else is a little less. So we'll try graphing that. There we go. And the third one we want to graph is the inverse. Y is equal to 1 over cos squared x. So a few things we've got to recognize here. If the point on the graph here is 1, they're not going to move, because 1 over 1 is equal to 1. Points like, oops, I'll just mark those in. Points like this though, that are fractions, well, 1 over a fraction is going to be greater than 1 if a fraction is less than 1, because 1 over 1/2 is equal to 2. So these points here are going to jump up. And the really tricky part about this is knowing what to do when the yellow graph equals 0, because we're going 1 over those values. Well, 1 over 0 is undefined, and we can think of those as asymptotes. We'll mark those in right now. There are the asymptotes. Graph starts here. The graph will jump up and shoot up to infinity, and then coming down, symmetrical around pi, and continuing on. And the graph we've just drawn is the same graph we have up here. So that's how we get to 1 over cos squared x. Let's look at now the formal rules for derivation when this gets a little more complicated. We have y is equal to a tan b x plus c. dy dx is going to equal a times b over cos squared b x plus c. So what's inside the bracket of the cos squared down the bottom is what was inside the brackets for tan. And of course the b usually gets multiplied out the front in these cases, the exception being the log. So for example, we could have y equals √3 tan pi x take 2, c equals -2, b equals pi, a equals √3. So going by the formula we had just above, dy dx is equal to √3 pi on cos squared pi x take 2. Now this form I've drawn in here, you can see this b value is multiplied to both of these inside the bracket. One thing that pops up occasionally is the form I'll draw over to the far left here. It could be y is equal to a tan bx plus d. So the b is outside. Well, the derivative of this is equal to, similarly, ab over cos squared bx plus d. So following rather the same rules we spoke over here, whatever's inside these brackets appears inside these brackets. So we could have, for example, y equals 5 tan 2x take 1 dy dx is equal to, well, a is equal to 5, b is equal to 2, c equals negative 1. So this equals 5 times 2, 10 over cos squared 2x take 1. Now, as far as the very simple derivation goes, that's the end of their lesson. But some people are curious as to how y equals tan of x could have a derivative 1 over cos squared x. So if you're watching this lesson and you've already moved on in the methods curriculum to look at the product rule or the quotient rule, you'll be able to follow along for this part. I'll derive that to the top left here. I'll just border it off with the yellow line. So we start off with, I'll do it in yellow. We start off with y is equal to tan of x, and the first thing to do is recognize that tan of x is equal to sine of x over cos of x, and we say, well, let u equal sine of x and v equal cos of x. Now this might seem strange unless you've done the quotient rule, but if you have, if you have done the quotient rule, you should be able to follow on. U is equal to sine of x, so u dash is equal to cos of x, and u dash is short for du dx, but I'll just write u dash and v dash from now on. V is equal to cos of x, so v dash is equal to negative sine of x, as we've discussed in the past videos. Therefore, dy dx, coming down from here, is equal to v u dash take u times v dash all over v squared, which is equal to cos x take sine x multiplied by negative sine x all over cos x squared, which is equal to cos squared x plus sine squared x all over cos squared x. And this top term, this top expression, is an identity, and that just equals 1. So equals 1 over, I'll just underline that, equals 1 over cos squared x, which is what we have down here.